Uh, Thanks, Zapfan. I'm trying to think what I can do about this. Apparently, Pamela left the astronomy cast stream going. Didn't shut it down. Hopefully, that'll get her to do it. Thanks for the fix. Okay, I'm going to be organized and record right away. Excellent. And then let's make sure we got the new white balance Chad. There's this and this. Okay. All right. Hey, everybody. Welcome to another episode of the live question show. Now it is 5 p.m. Pacific Daylight Time. Next week, it's going to be 10 p.m. Pacific Daylight Time, which will work out to mid-afternoon in Australia. If I really wanted to be organized and do this correctly, I would do it at midnight. But I am not going to record my show at midnight. I can't do it. I'm sorry, Australians. I cannot cave and do the show at precisely the same time. I'm too sleepy at midnight. Midnight to 2 a.m. I don't know how Zapfan does it. And John Seffel. You guys are beasts. Bill the dog. Thank God I need a break from politics. Oh no, it's going to be an all political episode. I'm just going to rage against my various local city councilors here in the city of Courtenay, British Columbia. So I'm just going to go through each one and just detail their policies and how I disagree with them about zoning ordinances and garbage pickup days, things like that. So you're warned. No. So what are we looking at here? You have stumbled into my weekly question show where I'm going to be answering your questions about space and or astronomy. This show lasts for 2 hours. Now, you are not obliged to stick around for the entire 2 hours, but, it's just polite, right? We've got to push those numbers up. We've got to convince YouTube that having actual human beings do live streams here on the channel is a value. And so, I'll let you have a bathroom break at the halfway point. Maybe we can all go grab a snack. But otherwise, you're locked in for 2 hours. So go ahead, put any questions that you have about anything into the YouTube comments. And then the moderator and his trusty AI buddy, Zapfan, will grab those questions and put them into the database that I will then be able to read, in theory. Now, just put your question in once. Please don't put it in multiple times, hoping that you'll finally be able to get my attention. The way this works is that it just makes this big list, and then I'm able to look through the big list and figure out the ones that I want. And if you ask the question multiple times, it just gets ignored. And in fact, it makes me mad. You don't want me angry. You want me happy. And then if you keep the question short, which, is usually not a problem here when we're just typing questions into the YouTube comments. So a couple of ground rules. And the first one is just a reminder that I am not a scientist. I'm just a journalist. I am merely a conduit through which the scientific consensus can speak to you. And so if you want my opinion about something or some theory or someone's idea, I cannot provide you any information. I can only report. I am not equipped to have ideas and opinions about some stuff. The second thing is I try to give emphasis to the people who've never had your questions answered before. So if you're long time watcher, now you need to be the first time asker, which is go ahead and put your question in. And if I don't see if I see that you've never had a question answered before, my eyes are just drawn to your question automatically. and I will try to answer it. And then the last thing is, your question might be there and you've never had a question answered before, and I don't seem to be answering it, and it's not personal. It is just that either we've answered that question so many times in the past that the regular audience is just super familiar with that, and I'm just going to try and give that question a break this week, or I don't know the answer. But we've got a new system that we're going to be trying out, which is that I'm going to try to make a mental note. I'm going to like literally grab your question and go, I don't know the answer to this question because I don't have time to do the research right now. And then hopefully it'll be like, Future Fraser here. I just did the research and here's the answer to your question. So that way I can still get around to the questions that I don't feel confident answering with just off the top of my head, because this is all off the top of my head. Okay. Don't answer silly questions. All right. So if you think I'm red, is that my white balance button? No. Hold on. Is that it? Nope. Yes. Okay. You tell me the white balance you want. Let's see. Ooh, that's the auto white balance. So we were using the auto white balance on the camera, but the problem is that it goes bright and dark automatically. So this one's a little warmer. Chad liked this one, but I agree. Like a little cooler. Now it's like brrr. It's icy. Now it's like weird. This isn't bad. This is cloudy weather. This is shade. Full sun. That's not bad either, actually. Oh, no, wait. That's auto white balance there. Or do we go around the horn? Auto white balance fish. Oh, I see. It's auto white balance for fish, which, might be right. All right. Let's go with this one. Did I change it? Okay. Okay. Scott Collins. Hey, Fraser, I'm about to order pizza. What should I get on it? Whatever you like. Pizza. Man, that is we make a pretty good vegan pizza, but cheese. Okay. Yeah, here we go. Let me look for a question here. Taco1011, reading the Dark Forest. Is it possible that an alien spacecraft visiting the solar system won't have a pilot, have no discernible outgoing radio transmissions, and will behave like the water drop? Okay, so that is very inside baseball here. We're talking about the Dark Forest, which is the second book of the Three Body Problem trilogy. And I would be spoiling if I explain what the water drop does. So I'm going to answer your question, which is it possible that an alien spacecraft visiting the solar system won't have a pilot? And yes, almost certainly a spacecraft visiting the solar system won't have a pilot. That if you want to be able to explore the entire galaxy, you need to leverage self-replicating robot probes, von Neumann probes, where you send a spacecraft out to the asteroid belt. It picks up all the raw materials, makes copies of itself, sends copies to all the various nearest star systems. They arrive at these star systems. They find the asteroid belts in those different star systems, make copies of themselves, go to other star systems. And that it's this completely automated process, which then has them explore the entire Milky Way. And when you consider the size of the Milky Way is, say, about 120,000 light years across, and we are like halfway in between the center of the Milky Way and the outskirts of the Milky Way. And let's say we were going to send a space probe that could go at 10% the speed of light, then it would just take about 1 million years for one spacecraft to multiply like bacteria, like fungus, like yeast, to every single star system in the entire galaxy. And then each of these, as the spacecraft arrives, it builds a big transmitter and starts sending home data. back to planet Earth. And then we are collecting in this giant database all of the planets, all of the stars, all of the interesting precursor artifacts that we find in all these different star systems, all of the alien life that we find. We just collect it all in one big database. And after 1,000,000 years, we will have completed the database, the Encyclopedia Galactica. We will know every nook and cranny of the entire galaxy. And that will be useful just for like our knowledge, or would be useful if we decided, okay, well, like what are the best planets? Which are the ones we want to send spacecraft to actually try and colonize and move to, or send settlers to. So there's real value to do that. And so one of the sort of thought experiments that you have is, because that's a thing that we are likely to do, then we would expect other civilizations to do that to us. Now, for those of you who are steeped in this idea, one of the big challenges is actually the keeping your spacecraft coherent over long periods of time, because you're going to be making copies, and that those copies are going to suffer radiation damage and so on while they're going through space. And so they're going to need to have some form of error correction. And so there was a paper that we reported on about a year ago where this is actually a big problem. If you're going to try and have a spacecraft that's going to be able to go for, a copy of a copy of a copy of a copy for 1,000,000 years, that it is going to start to decohere, and it's going to lose a lot of its programming just through cosmic rays. They're just going to be slamming into its memory system and giving it problems. And so we need to come up with some kind of a solution to make the spacecraft sort of able to handle that kind of long-term copy paste. And that's where we would look to life. Look at the way life is able to adapt itself to changes in its environment over time through evolution. It might be that we develop an evolutionary algorithm for our spacecraft so that they can then evolve as they move from world to world, and who knows what we're sending out into the cosmos. But yeah, that's a thing that we would expect. Would it move like the water drop? It depends on what your programming is. Read the book, for those of you who don't know what it's talking about. Blue water. When stars form a cosmic nursery, why do they not all gravitate towards each other and combine? Well, the question you're asking is not necessarily about the cosmic nursery. The question you're really asking, when you think about it, is like, why doesn't everything just combine? Like, why do all the planets go around the sun? Why don't they all just get sucked into the sun and combine into, well, it'll still be the sun with a few planets inside of it? Why don't all the stars in the entire Milky Way get sucked into the supermassive black hole at the heart of the galaxy? So yeah, when you start out with a stellar nebula, right, you've got this huge cloud of gas and dust, and it is turning in some rate. And then pieces of it start to collapse. And as the pieces start to collapse, it spins up, and pieces will kind of tear themselves off from each other. And then those pieces will start to sort of compress down, and you'll end up with what will turn into a star system. And the same thing that's going on here in the solar system is the same thing that's going on with these stellar nebulae, which is that they have a orbital velocity around each other. And so here in the solar system, the Earth is going at 30 kilometers per second in orbit around the sun. It's being pulled in by the sun, and yet its orbital motion is giving an outward force that are in perfect balance, and that leaves the Earth in orbit. The only way to get the Earth to fall into the sun is to cancel the Earth's orbital velocity. And so the same thing, if you've got a bunch of stars that are moving in some kind of interactive way, the only way to get them to actually come together is that you've got to cancel out that velocity. Otherwise, they're going to go into binary stars or sort of larger, more complicated operations. There's systems that have 8 stars in them. And the amount of energy that it would take to make those stars come together and smush into one is enormous. And so what sort of defines how many stars you have in that stellar nursery is just how much sort of overall angular momentum is in all of the particles within the cloud, and how it tears itself and breaks itself up into pieces, and how those pieces are able to orbit around each other and interact in the larger nursery. But it's a very chaotic environment. And so you will get these stars that will be pushed into binary star systems with each other, or ones that will be kicked out. In fact, over time, every single star within the stellar nursery is getting kicked out into the larger Milky Way one by one. And over a few 100 million years, the entire star cluster is dissipated into the larger Milky Way. David Meyer, if we achieved practical faster than light travel, what implications would it have for intelligent life? Faster than light travel is one of those paradoxes, in the same way that time travel is a paradox. So imagine time travel, because it's simpler than faster than light travel. Maybe not, same problem, but that here we are, we exist in the 21st century. We are 13.8 billion years after the beginning of the universe, but theoretically there is an infinite amount of time in our future, and that civilizations will rise and fall across the entire galaxy. And but when you have infinity, weird things can happen. Essentially, things that are possible start to happen more and more, and they'll happen an infinite number of times. And so if there's an infinite amount of time in front of us, then there should be an infinite number of time travelers showing up to visit us, to, they should be popping into this room, watching me record this YouTube channel. And that's, I'm not a very important person, and yet they should be everywhere. And the same thing goes for faster than light travel, which is right now, if we assume that the speed limit of the universe is the speed of light, then that defines really how quickly various civilizations can get to each other. But if there is the potential for faster than light travel out there in the universe, then there is no limit, that you could have aliens from hundreds of trillions of light years away being able to travel across space to other locations. And so what we would expect to see is aliens everywhere, right? Because if there's an infinite universe and there's faster than light travel, then they should be everywhere. So this is sort of one easy way to think about the potential of faster than light travel, is to say, well, if there was faster than light travel, we would see aliens everywhere. We don't see aliens everywhere. Therefore, it might very well be that faster than light travel can never happen. But if it was possible, I'm just leave it there. Yeah. So if it was possible, we should see more aliens, and we don't see any. So that should be a strike against either faster than light travel or there being any intelligent civilizations out there. Andrew Doctors Williamson YT. What is the furthest galaxy that we know of after Webb took over from Hubble? Oh, okay. What is the furthest galaxy that we know of after Webb took over from Hubble? So when Webb came online, it was immediately setting records for the most distant galaxies in the universe. The early days, if you can remember back, sort of summer of 2022. Wow. We were getting these distances. Now, astronomers measure distance using a term called redshift. And that if the cosmic microwave background radiation is 1,000 redshift, and then the numbers come down from there. And we were getting numbers from James Webb reporting things in the 10 redshift to 15 plus, even 17 redshift. And those correspond to times, essentially you're seeing the galaxy within between sort of 200 million years after the Big Bang to 400 million years after the Big Bang. Now, that was a very rough measurement that was made, and then astronomers got more time on James Webb, and they're able to do sort of deeper follow-on observations and confirm the spectra of the galaxies. And the spectra is the thing you need. It's looking at the light of the galaxy to tell you, you're essentially seeing how the various absorption lines and emission lines of the galaxy are being shifted into the red side of the spectrum. It's this chemical fingerprint. And once you can measure that chemical fingerprint and then you see how far it's been shifted, you can calculate how essentially how fast that galaxy is moving away from you, the redshift. And from the redshift, you can calculate the age of the universe that you're seeing that galaxy. And the record right now, and of course, this is September 2025, is a galaxy called JADES GSZ 14. So the name there is that it's a redshift 14 object. And the JADES is that it was gathered as part of the JADES survey, the James Webb Advanced Deep Extragalactic Survey. And so when you convert the redshift of it's 14.18, when you convert the redshift of 14.18 to years after the Big Bang, you get about 300 million years after the Big Bang. I think it's like 290 million years after the Big Bang. And so right now, that is the oldest galaxy that we know of. But we're still sort of pre-James Webb Deep Field survey. Webb is doing this survey, the JADE survey. There are other surveys that they're doing, but they haven't gone and done what they did with Hubble, where they pointed a spot in the sky that is seemingly empty and then just gather photons for hours, days, maybe weeks, and then use that to then sort of study what you see in that small area. And so almost certainly that record of 290-ish million years after the Big Bang is going to get broken in the future. The other way, and this will be sort of even luckier, is if there is a gravitational lens. So you can have the situation where there is a foreground galaxy or a galaxy cluster that is acting like a natural telescope lens to some object that is behind. And Webb has observed a ton of these. But out there somewhere, there is going to be the perfect lens where you've got this foreground object that is lensing this other object behind it that is much farther away. Now, there's going to be a limit to how far away you can see galaxies, because that there's this sort of time in the universe called the Dark Ages, where the universe was essentially opaque. It was sort of filled with fog. And that even if there were galaxies that were forming, they were surrounded by this fog that didn't let any of its light escape. And so we wouldn't be able to see it. So we will reach this point where we will find the farthest possible galaxy, and it will be some number. And we're not there yet, not there today, but I would say by the time Webb has reached the end of its life, there will be this number. It will be the farthest galaxy that we've ever seen. It will probably stand as a record for the test of time, and it will pretty much be the farthest galaxy we possibly can see, because we can't see through the Dark Ages. It's just, on that day when you had this really thick fog around you, you couldn't see out. And that entire universe was like this really thick fog. And so we won't be able to see through it using a telescope like James Webb. Now, there's other ways to look through that dense fog, but maybe that's a different video. CK Coffee. Didn't know you do QA live sessions. Yeah, we turn the QAs, we hide them after, so they're not on the channel. But yeah, we do this every Monday for 2 hours. Brendan, Thigpen, what is the latest in anti-gravity? Are we making any real progress? So there is no anti-gravity, and we are not making any real progress. Nobody has come up with any possible way to come up with anti-gravity today. The last hope that we had for anti-gravity was that antimatter would experience anti-gravity. And this was like one theoretical possible way that this could work. Now, you take regular matter, you reverse the charges, you get antimatter. You combine regular matter with antimatter, it explodes, annihilation. And so it was theorized that maybe that antimatter would fall up in a gravity field. It was this, by no means this was assumed that this was going to be the case, but it's really hard to take one single, say, proton and then drop it in a gravity well and then make sure that it is actually falling down and not falling up. And it wasn't until a year ago or so that scientists were able to perform the experiment with a level of certainty to rule out that antimatter falls up, that antimatter experiences anti-gravity. So antimatter experiences normal gravity just like regular matter, which is what you would expect. And so that as a possible route to get to anti-gravity has been ruled out. So right now, we don't know of any way to make anti-gravity to repel. And there are thoughts that if you could get your hands on negative matter, negative energy, that you could somehow produce anti-gravity. But for now, it's purely science fiction. KGS, is that fog made out of hydrogen? Yeah. So hydrogen and helium, molecular hydrogen and helium, cold hydrogen. So I guess this is going to turn into more of the question. So, in the beginning, we have the Big Bang, and then we have the cosmic microwave background radiation where the universe becomes transparent for the first time. And you've got all this hot gases, plasma, left over from the Big Bang, about 380,000 years after the Big Bang. And then all of that gas starts to cool down and goes through different levels of coolness. And you can't get stars out of hot gas. You need cold gas to make stars. Once it's a plasma, once it's really hot, it doesn't want to collect together into stars. So the entire universe was sort of, expanding apart. All of the clouds of gas from the Big Bang were cooling down. And it wasn't until within the first, say, 50 to 100 million years after the Big Bang, after the cosmic microwave background radiation was released, that the universe had cooled down to the point that the gas became molecular again, no longer a plasma. And then now you can get stars. And so these stars are starting to, the clouds of gas are starting to find each other, starting to pull into these larger and larger objects, turning into the first stars. But now the first stars are surrounded by all of this cold molecular hydrogen. So even though they're shining, you can't see them because the molecular hydrogen is opaque. This is what you see when you look into this is what you see when we see like cold molecular nebulae. There are these dark nebulae, and they are molecular hydrogen. They are obscuring our view into them. And so the entire universe was like one big dark nebula, but there were stars inside of them, which can be inside dark nebula too. Anyway, and so those first stars were putting out ultraviolet radiation and starting to blast away gaps and openings in these clouds of molecular hydrogen. And finally, you got all of the radiation coming from the stars, both sort of pushing this material away and heating it up, all the leftover hydrogen, that you get this age of reionization, this time when all of that gas got hot enough again that it became transparent again. And so we're able to then start to see those first stars and galaxies. There will be this time in the universe when that happens. Supex Andrew Kirkpatrick. Can a black hole have a planetary system where the planets are far enough away from its gravitational pull that they are able to orbit the black hole safely, including stars and such? Yeah, absolutely. If you replaced the sun with a black hole with exactly the same mass as the sun, then the planets would just continue to orbit around this black hole sun for the same amount of time. Probably longer, because now the sun isn't going to be, the black hole isn't going to go through the end of the star the way that the sun will. So you could have the stars going around the black hole sun for billions and billions and trillions of years. As long as nothing came through to disturb the system, it would last forever. And so theoretically, there are black holes out there where the planets are far enough away that they're in a planetary system around the black hole. Now, it's not a great place to be because you're not getting any radiation from your star, but you're at least stable. People have proposed that this is a really good way to organize a solar system, that, you put a supermassive black hole at the heart of your system, and then you bring in stars and you put them in orbit around the black hole in a way that is stable. And then you could put planets around those stars, moons around those planets, and you could have systems that have multiple black holes, multiple supermassive black holes. You could have thousands of stars with 10,000 planets all in one big elaborate system. Theoretically. So a black hole is not like a vacuum cleaner. It is just a thing with mass, like anything. It's only when you get really, really close to a black hole do things get weird. Do you experience the time dilation? Do you experience the extreme tidal forces? But once you're far enough away from it, still trapped in its gravity, everything is fine. Answer that question. Okay. CK Coffee. I don't know why you mentioned. Okay. CK Coffee. Don't know if you mentioned the Breakthrough Starshot project today, but I was so sad to hear that it was quietly shelved. What's our next chance for such an interstellar journey? So this was a news story that I mentioned on Space Bites last week. Story written by Sarah Scholes about the status of Breakthrough Starshot. And this is something that I think those of us in the community had expected was coming for a while now, which was that it had just been kind of quietly shut down. It never released very much money to, it was expected to give $100 million to researchers to try and develop an interstellar probe mission. And in the end, it only gave about $3.5 million to various people. And it's sad. It's very sad because I think it was one of the most exciting ideas that we had seen in sort of space exploration in a long time. That, there's a lot of really exotic ideas about how you're going to go and travel to other star systems that people have proposed. Fusion drives, the Orion, where you're dropping bombs out the back of your spacecraft. But in the end, really, the only two viable ideas for being able to go to another star system are either an antimatter drive, and we don't know how to produce an antimatter at scale, and we don't know how to hold it, and we don't know how to use it in a way that powers your spacecraft. The other viable solution is a light sail or a laser sail, where you don't carry propellant on board your spacecraft. You just fire at it with a laser that accelerates it up to high speed. And that sort of the idea that was brought forth with Breakthrough Starshot was to build these solar sails really small, just a few meters across, and then make the spacecraft itself just a little tiny chip. And that you could send a fleet of these things and they would be able to visit another star system within a human lifetime and be able to send back information. And you had a lot of luminaries who joined the announcement. You had like Seth MacFarlane, you had Stephen Hawking, you had Avi Loeb, you had Mark Zuckerberg. Like, there's a bunch of people involved in this, as well as the funding from a genuine billionaire who was so excited about the idea that he was willing to put down theoretically $100 million of his own money to make this happen. And what it showed with the amount of press that they got was the pent up desire for humanity to do something special, for us to have the moonshot of our generation, to send a spacecraft to another star system, to realize the dream of all of this science fiction that we have been consuming for decades, 100 years. And it's so heartbreaking that it turns out the money wasn't distributed in the way that it was expected, and that nobody told us. It's like you're following a leader across some difficult journey, and the leader just kind of slips off out the back when no one noticed, and you're still walking, and then you're like, wait a minute, where are we going? Because the leader's gone. And I think that demonstrated the public enthusiasm for this. And so I think if anybody who is wealthy is watching and listening to this, or, that demand is still out there. And if you want to make a big impact on the sort of harness this enthusiasm across so many layers of society to send a spacecraft to another star system, to give us that first up close glimpse of what it would look like in another star system. When you consider the amount of money that's getting spent by NASA, by ESA, by JAXA, by the Chinese, you're looking at tens of billions of dollars every year to keep various space hardware operating, to build probes, to build a helicopter for Titan, things like that, right? $100 million is actually not very much. That is chump change. That is the price of one small mission for NASA, one small mission for ESA. And yet, the amount of goodwill and public relations that got is incalculable. And imagine if some space agency, some group pulled those funds together, backed by a billionaire who was going to keep writing the checks, and very carefully and very intelligently actually continued the progress. And it might not be a thing that will come together in our lifetime. Like, it's almost certainly a more complicated problem than we are expecting, than science fiction has led us to believe. But just the doing, the putting our minds to this process of trying to pull together the best and the brightest across the entire planet to solve this challenge is worth doing. And it will pay 100-fold back to human society in the engineering that's discovered, in the bonds that are forged, in the new relationships, the new connections, in the things that we discover. And it has this incremental value. So it's not just, if we make it to another star system, then the payoff is there. But the reality is that this technology of using laser sails to explore inside the solar system would completely change the way we explore the solar system. That you could send tiny little solar sails off to every single comet, every single asteroid, every single moon, all of the planets. You could send tens of thousands of these things within the solar system and learn a tremendous amount about and practice. So we have the ways to practice in the near term. All of these technologies have value across our entire society. More powerful lasers, better solar sails, miniaturization of technology. Like, the benefits are there. It's just, and that this is the most viable idea that anybody has ever thought of. And so this is a thing that we should continue to work on. And it sucks. Like, there's this idea where it's kind of like a FOMO, sort of, where when you discover that somebody is doing something that you're excited about, then you sort of go, okay, well, so the problem is being solved. I don't have to think about this anymore, right? The sending humans to Mars. Oh, Elon Musk's got this figured out, then I don't have to do this, right? And maybe his idea isn't going to work out. And all this time spent waiting for for them to accomplish it is time that could have been spent working on it in other ways at the same time, and that it takes many different ideas all at the same time. And so I think my perception was that sort of Breakthrough Starshot became this sort of place where people focused their attention on, that they were the ones that were doing it. And so everybody kind of took a back seat. Like, a lot of people work on really interesting projects and a lot of technologies moving forward, but it really feels like we were waiting for them to carry the torch forward, and they didn't. And so now somebody's got to pick up the torch and start carrying it forward. But for real this time. So yeah, I think that that's the part that's so disappointing. And I think, like, if I was going to do it, I would probably make it much more transparent. I think that, we learned some announcements of various things that had gotten funding, but I think the way you do it is you make the whole process, like, try to get as much crowdfunding as you can from people to be donating, try and bring in grants, getting government projects and so on like that, so on and so forth. And then have some website where people can see all of the projects that are working on right now and how they're working out, and they can contact the researchers and they can see where their money is going, and people can come together for town halls and discuss the various pieces and discuss the technological readiness levels, and turn it into this giant community of enthusiasts and engineers and scientists and people who are funding this, that are moving the whole thing forward, and not just this, a couple of people are working on this, they've probably got it under control, I'm just going to wait for them to solve it. That's not going to work. It's got to be this giant, transparent, collaborative process, in my opinion. So I was heartbroken when I read the article, and yet it was just terrific journalism. And hopefully somebody else will pick up the torch, and we will continue on with the incredible dream of sending a probe to another star system to take pictures up close. Aaron Sokol. A few years back, I saw a fireball streak very rapidly across the sky and explode right near the full moon. It was brighter than the moon, and I briefly saw pieces flying off. How big was it? So you might be surprised to learn that when you see a shooting star, a meteor, they're actually very small. So, like, when you go outside and you watch, say, the Perseids meteor shower, and you see this incredible streak of green that goes for half the sky, that thing is probably a little bit bigger than a piece of sand. And when they get bigger, maybe a couple of centimeters, maybe fist-sized, that's what you probably saw. Those are fireballs. And they can be, up to about a meter. Once you get to the meter size, then they turn night into day. They're really dramatic. But what you saw, probably in this size, probably smaller. And yet there's so much energy in those meteors as they're entering the atmosphere that they just cause that enormous sky show. Fireballs are rare. I've seen one in my life, and I've watched a lot of meteor showers. And hopefully, like a lot of people who are watching this right now, you've experienced this time. Like, if you're lucky that the whole landscape turns to day or is very lit, and you can see it snap and crackle and pieces pop off and like kind of breaks into chunks as it's entering the atmosphere. And that's how you know there's something pretty serious. But, enthusiastic astronomers can spend their whole lives and never see a fireball like that. So congratulations. That's really lucky. Brandon Thigpen, how do we have anti-gravity patents but no anti-gravity applications? I mean, I'm not sure how a person can have an anti-gravity patent. You've got to prove that you've produced anti-gravity. And so to get a patent, right? Or at least you've got to like show in your patent that your mechanism is probably going to work. So I can't imagine that there is an actual practical anti-gravity patent. And if there is, then just make it. Someone needs to make it. And I bet they can't. Like if there are I'm sure in the patent office, there's people who are like, oh, someone's proposing something that violates the laws of thermodynamics. You can't have a machine that can run forever, and you can't have anti-gravity. So might be that maybe they haven't like properly disclosed they're trying to have anti-gravity. So yeah. I mean, if someone can make anti-gravity, they should make anti-gravity. Anti-gravity would change the world. Anti-gravity would be a trillions of dollars technology. It would change everything. But nobody has because they can't. Jay Lambert, why do scientists seem so skeptical that fish or larger life... Jay Lambert, why do scientists seem so skeptical that fish or larger sized life couldn't be in the salty oceans in the solar system, perhaps in the oceans of Europa or Enceladus? I always make the joke that we want to go to Europa to meet the European space whales. But the reality is that there are going to be things that are going to limit the size of the life, the amount of biological material that can be present in Europa or Enceladus. And I haven't heard the specific calculations on Europa or Enceladus, but I have heard the calculations on Titan. And Titan is another world like both Europa and Enceladus. It has a subsurface ocean, a thick layer of ice. It has, it's the second biggest moon in the solar system. It has probably subsurface volcanoes that are spewing gas and chemicals into the water, and then you've also got all of the organic molecules that are on the surface of Titan, and they're probably finding their way down through cracks into the ocean underneath. You have all of the raw material that you require for life. But the question is, how much energy is being put into the system that then life can use? And the problem is there's just not enough. There's not enough usable energy. When we are here on Earth, we are experiencing something like 1,000 watts per meter. I forget the exact number. It's roughly that. An enormous amount of energy. And then that allows plants to grow. That allows animals to eat the plants. That allows bacteria. That allows all of this kinds of life, because of the huge energy density that we're experiencing here on Earth. If we changed the sun to a red dwarf star, and now it could still be warm enough, but the wavelengths of the light would reduce the amount of energy density that's available on the surface of the planet. And we might not even be able to have plants grow under red dwarf light, or it would be a reduced amount of life on the surface of the Earth. But when you're looking at just pure chemical energy that you're getting from volcanism, it's not very much. And so people calculated that I think it was it like a cat, a dog, a small dog, that you could have the equivalent amount of, so you could have 10 million bacteria or one small dog. That's how much life would be supported by the chemical energy that is going into the subsurface oceans on Titan. And so you can kind of assume it's probably the same on both Europa and Enceladus, that there's just not a lot of energy. And so you just aren't going to get microbes growing near the volcanic vents, fish eating those microbes, being eaten by bigger fish, and then of course becoming meals for the European space whales. That you don't get bigger than bacteria, but even bacteria would be amazing to find. And so that's why people are skeptical, is that there's just not enough energy available for life to grow into larger body sizes. Dammer Zed, could a gravitational slingshot be possible to exceed the speed of light, like a black hole slingshot versus a star slingshot? So, like, rule number one is that you cannot go faster than the speed of light. Rule number two, read rule number one. Refer to rule number one. So you can't go faster than the speed of light. So even if you could receive an almost infinite amount of energy from your gravitational slingshot of a black hole, you can't go faster than the speed of light. What you'll do instead is you will be putting an infinite amount of energy into your acceleration, and you will get closer and closer to the speed of light, and it will take an infinite amount of energy to get you all the way up to the speed of light. That's just the iron law of the universe. And so there's no idea that you can use that will allow you to go faster than the speed of light. Like, unless we figure out a warp drive, no, you could burn all of the fuel, all of the hydrogen in the entire universe in one big fusion drive, and you won't go faster than the speed of light. You could turn all of the universe into antimatter, and then, or half of it into antimatter, and then combine that antimatter with matter, and you're not going to be able to go faster than the speed of light. And you could do a gravitational slingshot around the most supermassive black hole, ton 618 or whatever, and you won't go faster than the speed of light. You go very fast, though. You can go very close to the speed of light, but you can't go faster. And, you know, we have particle accelerators here on Earth where they are accelerating protons to 99.9999, you know, some huge number of nines percent the speed of light. That those protons are experiencing time dilation in the particle accelerators, but they can't go faster than the speed of light. You can't accelerate a single proton faster than the speed of light, even if you use all of the energy available in the entire universe. You're still going to go slower than the speed of light. It's going to be very close, but that's the rule. Where are we at? Okay. Santiago T. I understand how gravitational lensing causes warping of space and thus light gets bent. What I don't get is where the magnification comes in. Could you explain it? Sure, it's the exact same way that a lens works or that a mirror works. That, you know, if you imagine some object, a tree, right, is really far away, and it's, you know, photons are coming off of the tree in all directions, and then you put a lens on your side. You're taking the photons that are coming off the tree that would have missed your eyeballs, and you're redirecting them back into your eyeballs. And so you're seeing more photons than you would normally be able to see with just your eyes, because, well, your eyes are lenses too. But anyway, so because the bigger the mirror, the more of those photons that would have missed you, you're now redirecting in. And it's the same thing. A galaxy cluster warps space around it so that photons that are traveling, that would be sort of moving away from us, have to follow this curved path around the galaxy cluster and converge back on your eyes. And so you get this magnification process. It's right there in the name, gravitational lens. Oh, is it time? Eric Poot. Hawking says black holes will evaporate when particle-antiparticle pairs pop into existence at the event horizon, and only antiparticles drop down into the black hole. Wouldn't the split be even, keeping the black hole stable? Okay. It's been a while, so I think I should do this, but you guys are all going to have to buckle up. All right? Buckle up? Okay. So this idea of Hawking radiation, that you've got this black hole, the event horizon, you've got virtual particles that are popping up at the very edge of the event horizon, and normally those virtual particles come together and annihilate, but in this case you've got a black hole, one falls into the black hole, the other is able to escape and go out into the universe. This somehow makes the black hole evaporate away because you can't have matter appearing out of nowhere, and the black hole has to give up some of that material. That is a lie. It's not a lie. It is a bad thought experiment that Stephen Hawking gave, and knew that it wasn't a good thought experiment, but he wrote a book about it, Brief Moment History of Time, and it just stuck in the public consciousness. And so we get these kinds of questions from people because, like, obviously the idea that Hawking is putting into your brain is starting to come apart at the seams, and you're like, I don't get these pieces. How can light be coming off of the black hole, and yet the black hole's getting smaller? I don't really understand. And okay, so that's not what's happening, and that's not what causes a black hole to evaporate. So I want to take you on a journey of a completely different way of thinking about Hawking radiation, one which will make your question irrelevant, and yet is a much more accurate picture of what's actually happening and what's causing a black hole to evaporate. So the first thing we have to consider is this idea that space is filled with fields, and that, you know, there's various fields that are associated with all the different particles, and that when you accelerate through space, through fields, you experience radiation. And it's called Unruh radiation. And this is just like one of the intrinsic properties of space. As long as you're accelerating through space, you are experiencing radiation. And we know that the equivalence principle says that you can't know the difference between accelerating or free falling. That, you know, in a gravity field, that you can't tell whether you are sort of floating in space or whether you are accelerating down into a gravity field, that the experience is equivalent, right? And there's no way to tell the difference. You know, if you are in an elevator and the elevator is like the TARDIS and it is accelerating through space, and because it's accelerating, you are experiencing the force of gravity on the floor of that elevator, and it feels just like exactly like gravity, or the elevator is sitting on the surface of the earth and you're experiencing the same amount of gravity. And there is no way to tell the difference. That is because the acceleration through space and the acceleration caused by being in a gravity well are equivalent with each other. And so when you take that idea of them being equivalent to each other, you have to take that to all of the different ways that these things play out. And one of these is that Unruh radiation, this idea that when you're accelerating through space, you experience radiation. And so when you are in the presence of a gravity well, you are experiencing radiation that is coming in the exact same way as when you're accelerating through space and time, space-time. And this effect is non-existent. But when you are, you know, very close to a black hole, an extremely dense, massive object, then this radiation can become present, or, you know, detectable, theoretically. And that, I'm trying to sort of finish this off. And so back to that sort of idea that of what Hawking was saying was that, you know, you've got this radiation, it can't come from nowhere, and nobody's moving, right? Nobody's accelerating, nobody's expending energy to move through this gravity well, or nobody's experiencing energy, you know, caused by this gravity well. And so the black hole has to give up some of its mass to create that energy, that Hawking radiation. And so over time, the black hole gives up more and more of its mass, turns it into radiation. And the amount of radiation that you experience is inversely proportional to the mass of the black hole, because the most radiation is given in regions of high, sort of like a high change. That's probably too much detail. That'll do. All right. So that is the sort of the answer. And so when I go back to your question, you can see it doesn't really matter, right? That there are particles, mostly photons, that are coming off of black holes that are the result of this sort of equivalence principle that force the black hole to give up mass. And the thing that's really interesting is that this Hawking radiation probably happens to everything. It probably happens to neutron stars. It probably happens to white dwarfs. It probably happens to us, that on the scale of 10 to the power of 100 years, we will evaporate because of the gravitational potential of our mass. Whew. All right. That is we'll do this again in the couple of months. KGS, do you think that space opera is a subset of science fiction? That's a tricky question. So, like what is science fiction, right? Speculative fiction. And so you are speculating on a galactic civilization, people flying big ships, traveling from star to star. It is absolutely science fiction, speculative. So yes, I think, could you have a space opera set in a fantasy world? No, you would just have a fantasy story. So why is space opera a subsection of science fiction while fantasy doesn't have a subgenre that is equivalent to space opera? Is that just because all fantasy is essentially space opera but with elves? I don't know. Is it its own genre? What does it even mean to cut up genres like this? I'm going to be puzzling this question for weeks, I think. I'm drinking water, but from titanium bottle. So only the best aerospace materials for my water. Christian DeSalio, Fraser, what do you have just beyond your screen? Can you flip your camera around for us? I can't flip the camera around for you because if I did, I would never be able to put it back. But what's in front of me is my window in my office. So, and I've got a blind down to block it. And then I have I have my storage shelves right here. I've got some metal storage. And then my desk, storage over there. Yeah, it's not a very big room. It's 11 by 11 room, 3 meter. It's about a 3 meter by 3 meter room. So it's not a very big room. So speaking of Dungeons and Dragons, I'm, as you may know, I'm the dungeon master for my kids and their friends, my adult children in their early 20s. And so I bought I bought a little dice tower so you can roll dice in it. And then, but it came with really crappy dice that are really hard to read. And we're sort of like in a darkened room and I'm like rolling the dice and I can't see the numbers because I've got these old eyes. And so I bought 25 millimeter honkin' big dice with really clear numbers on them. So I bought my old man about my old man dice. Look at this. Now I'll know when I'm killing the players. What lens am I using? It's a... Man, I forget the number of the lens. I feel like I never even touch it. Hold on. It's an f 2.8 28 to 75 millimeter Sigma lens. Yeah, on a Sony A7 III. A7 III? A730? A370? I forget. The sort of low end but proper video camera Sony. Is that a blurry jar of Vegemite? The top shelf in the background? No. Oh man. It's like I've shown all the things on the shelf, so now we kind of come back around, I guess, for the new peeps. So this is ash from Mount St. Helens, and it's a honey jar. So I have family in Portland, and when Mount St. Helens went off, and there was just ash raining down everywhere on the streets in town. We even had it in Vancouver. It was just like it was snowing ash after Mount St. Helens went off. And so they scooped up a bunch of ash and gave it to me. And then I gotta have it so it doesn't go after my eyes. So I've got a piece of pumice from the ash. So there we go. We're back around to the beginning. What's on the shelf? This is the first thing that was on the shelf. I guess we go around the horn, or I get new things. Oh, what does it taste like? Yeah, man. I don't know if you've ever been to Mount St. Helens. It's a crazy place. I've been there a couple of times now, and it's bonkers. Just to see it's all recovering pretty well, but still, like, just the devastation that came from that volcano. Amazing. And we heard it. It was this loud kaboom that we heard. And I am hundreds of kilometers away from where Mount St. Helens went off. It was very loud. Okay. No, I don't have cats. Homestead Paradise. Hello there, fellow Canadian, longtime listener, first-time questioner. How are humans going to survive the radiation emitted by the sun when we inevitably leave to explore Mars? So we know that when you go to space, you are experiencing a couple of hundred times as much radiation as when you're experiencing down here on Earth. We are protected by the magnetosphere. We're protected by the atmosphere. Once you leave the protection of that, then you are just experiencing that radiation. And the radiation from the sun is a problem, especially if there's a solar storm. You can experience enough in a really powerful solar storm to give you a lethal dose of... You can experience enough radiation in a really powerful solar storm to get a lethal dose of radiation, and you just die. So when you think about some of the really powerful solar storms, when we see these really cool auroras in the sky, when we see these incredible flares and coronal mass ejections coming off the sun, those could be lethal to astronauts. But the more insidious one is the cosmic rays, because they are nonstop. So you don't have to sort of time things. They're just happening all the time. And the energy from the cosmic rays are much higher than the energy coming from the radiation particles that are coming from the sun. And so there are different ways to mitigate both of these. The solar storms, the plan is to build a fort. In the Orion capsule, the astronauts have a whole bunch of material that they can use. They have water, they have food, they have all kinds of scientific equipment, and that they have been trained to create a protective area inside the Orion capsule to protect them from a solar storm, to decrease the radiation load that they're experiencing while this solar storm is happening. But the cosmic rays, there's no way to stop them. That, with the amount of stuff that you have available, you just are experiencing this constant damage to your DNA from the cosmic rays. And that will sort of inevitably lead to higher rates of cancer down the road. So what can be done about it? Well, the only solution is that you have to put a lot of protons between you and the radiation, about a meter of protons. So a meter of water, a meter of rock, a meter of metal, whatever you want, just get that material in between you and space. And the problem is those things are very heavy, that, if you want to surround your spacecraft in a shell that is a meter thick of water or rock or metal, then that's an enormous amount of weight that you're having to then accelerate. When you consider the, if the Orion capsule weighs, I don't know, 15 tons, I don't know exactly what it weighs, around that, 10 tons, 15 tons, 20 tons. Anyway, you'd be looking at hundreds of tons more to surround yourself with water. So the plan is that there is no plan. The plan is that the people who are going to be the first human explorers to Mars are going to be brave explorers who are going to be subjecting their bodies to large amounts of radiation and are hopefully going to be rolling the dice and not getting large amounts of cancer down the road, are hopefully not going to experience a lot of solar storms that also give them acute radiation poisoning. Space is hard and dangerous and scary, and that we need to understand that anyone who is willing to make that journey is going to be taking an enormous risk. But for a lot of people, that's totally worth it. They don't, cancer is future me's problem, not today me's problem. So off to Mars we go. Oh, that's cool. Canadian Space Advocate, going to go watch the launch in Newfoundland in the morning. That's awesome. Keep me posted. We're going to report on it, but that is amazing. Amos Beck, do you know or have heard anyone planning to reach out to third parties to keep Chandra alive and running? No. Nobody is planning to, right now, keep any of the missions alive and running. That said, it looks like right now the plans are that NASA is going to run with the House budget and not the White House administration budget. And the House budget largely keeps NASA's funding the same. And so, although there will be some cuts, especially to some of the science missions, and there have already been thousands of senior people who have been kind of pushed out, bought out, that we're probably not going to see the cancellations of all of those missions unless the White House really puts the boots to Congress and forces them to accept their budget. So hopefully, fingers crossed, we won't see all those cancellations, but I'll keep you posted. Piznops, can satellites be seen with the naked eye? Absolutely. If you live in dark skies, I live in dark skies, and you go out any night, and right away you're like, satellite, satellite, satellite. Generally, they're very dim, but the International Space Station is incredibly bright. It's as bright as Venus. It's like the brightest object in the sky after the sun and the moon. And you can't miss it. You can see it in super light polluted cities. So what I would recommend that you do is there's websites that'll tell you when the International Space Station is going to do a flyover of your area. And, depending on where you live, how much far north or south, it's visible from a huge chunk of the earth. And you go outside, it's like a magic trick. You're like, hey, everybody, want to see a magic trick? There's the International Space Station. And then it just, we'll see it in 1 minute. And then the space station comes over the horizon and goes across the entire sky. It takes about a minute to go all the way across the sky. And it's very bright. So in darker skies, you can absolutely see satellites, lots of them. And like I remember as a little kid watching satellites. And at some point it sort of switched from this is really cool to these are stupid things that are getting into my astrophotos. Case K.S. Albrecht 88. What is the theoretical timeline for the universe to expand to the point where all external galaxies and their light become permanently unreachable and invisible from any local point of view? So the universe is becoming less dense over time. The distances between galaxies is increasing, and there will come a time in the future when galaxies will fall over the cosmic horizon and redshift away and be harder and harder to see. Now, there won't be some specific date that this is going to happen, but right now, the reachable universe is only about 4% of the universe, and that number is getting less and less over time. So there will be some time when the only universe that we can reach is our local group, Andromeda, M33, a few hundred dwarf galaxies, the Milky Way. That's it. Everything else will be accelerating away from us too fast for even if we traveled at faster than the speed of light, or if we traveled at the speed of light, we couldn't reach them. And so, I've heard the number like 100 billion years thrown around quite a bit. So in 100 billion years or so, you will go outside, you'll be an astronomer and you'll go outside and there are no other galaxies in the sky. There's just the local group. Now, those galaxies are just still there, and if you have like a really powerful telescope, you can probably still detect them, or if you have a radio telescope, you can probably detect them for 1 trillion years. But when you think about how, there will be stars that will live for 10 trillion years. So there's stars here in the Milky Way that will definitely outlive the time when all of the galaxies fall over the cosmic horizon and disappear. And future astronomers won't know of when the beginning of the universe happened, because that history will have fallen over the cosmic horizon. Mark G5891, what did you think of Foundation finale? It's renewed for season 4, which will likely air in 2 to 3 years. Ouch. I thought it was fine. I mean, if you've read the books, the twist at the end, they took the twist and then they twisted the twist. And so for the people who knew what the twist was going to be, were robbed. And fine, whatever. It's fine. I was fine. I liked it. When I watch the Foundation series, I don't think too much about what I like about the Foundation books. They are two separate entities. There are some ideas in the Foundation series, the TV show, that I really like, that are vast improvements to the original book series. Like the whole idea of the Cleons being around for generations the way they are is such a clever idea. I really like that. Other ideas are weaker, but I don't get too torn up about how well it adheres to the original Isaac Asimov story. I sort of imagine, like, if it was actually someone tried to sort of adhere directly to the Asimov stories, it would just be like a bunch of guys sitting around in offices, smoking pipes, solving diplomacy issues. Like, it would be a very boring story. So they're doing everything they can with Foundation to make it more exciting and thrilling than what was in the original Asimov books. Like, the Asimov books were this sort of mind-blowing idea about how you could predict sort of in general what the future of societies will do, and then sort of mapping out those large-scale things in this very very bureaucratic, very boring way. But the ideas are so cool that you are really excited by it. The ideas are better than the execution of the Asimov books, but they're still some of my favorite books ever because the ideas are so strong. Well, the Foundation, the special effects were great. You know, they did the black hole bomb. Like someone watched a Kurzgesagt video and was like, oh yeah, black hole bomb. We're going to build one of those. That sounds great. You know, and he's shooting the planets with the black hole bomb. And like my wife was just like, shouldn't that take longer for the beam to get from where it goes to the target? Because things can't travel faster than the speed of light. Like, yeah, it would take 1,000 years. Not very impressive. So yeah, they're good separately. Watch them, read them, enjoy all of the media, and don't get too bent out of shape in how they're the same or they're not the same. Ernst Camps, do you think understanding dark matter is the way to unlock a higher tier of space travel, like warp travel? Well, we don't know what dark matter is. And so we don't know what the implications for dark matter are in just physics. You know, there is this tendency that when we discover the properties of some part of the universe, electromagnetism, different forms of radiation, gravitational waves, all of the various just basic discoveries that have been made about the nature of reality, eventually those give us practical benefits. And so it feels to me like if we actually could figure out what dark matter is, if we could isolate the particle in the lab and figure out what the particle does and how it interacts with other particles, then the race is on to use this in various ways. Maybe it has properties that are very useful and we just don't know what those are. Like, would there be something really useful for a particle that has mass but doesn't have a cross section? Maybe. But we don't know specifically what the application could be. It might just be that it makes for a better fertilizer. We don't know. Faster computers. It doesn't necessarily have to do anything with space. It just happens to be a thing that we observe in the large scale structure of the universe. But what its practical applications for the future of humanity, we don't know. Or there might be no practical application. That's you roll the dice, right? When you do basic research, you have no idea what is going to be the destination that you're going to be arriving at. The journey is the point. Joy Hoser, who is the GOAT? Chris Hadfield or Roberta Bondar? Chris Hadfield is the GOAT. I don't need to see more names. Chris Hadfield is the GOAT. Silver 831 call. Any thoughts on the Hellfire missile that bounces off a mysterious orb in the stunning UAP footage shown to Congress? Hellfire missile going through a balloon is what it looks like. Justin Kruger, whatever happened to T Corona Borealis? That was supposed to go off any day now. Yeah. What happened to it? Any day now. Any day. Yeah, it's Nova are like wizards. They're never early or late. They arrive precisely when they mean to. Steve Phelps, are ion rocket engines the future of interplanetary flight? Ion rocket engines are the now of interplanetary flight. So there are a lot of space missions for decades that have been using ion engines. The Hayabusa 2 mission is using ion engines. The Dawn mission used ion engines. All of the Starlinks are using ion engines. So there are a lot of really cool ideas for ion engines for future missions. And in some cases, you want like a really high kick, and so you go with a chemical rocket. Other cases, you want to be able to accelerate for a long time, and so you go with an ion engine. Or you do a combination of both, where you have a very fast accelerating chemical rocket, and then you switch over to an ion engine for the longer coast phase. There's a lot of really cool applications that can be done with ion engines that have been proposed. You know, if you have a fission reactor on your spacecraft, and then you bolt onto that a really high thrust ion engine, you know, something that can provide the thrust of 4 pieces of paper on your hand as opposed to 1, that you can have a spacecraft go into orbit around all 4 of the Galilean moons. You could chase down an interstellar object like Oumuamua or 3I Atlas. So, you know, there's a lot of really interesting applications that could be done with ion engines if you give them more power, more fuel, longer time frames. So, but they're already flying right now and are, you know, returning samples of asteroids back to Earth. And next, Hayabusa 2 is going to try to land on an asteroid. So, yeah, ion engines are great, already doing great, and the future is going to be great. Did we go to page 2? Not yet. Okay. Stephen Hill, shouldn't we have found Planet 9 by now, or has Virubin not been online long enough? Virubin isn't online yet. Virubin is still in the testing phases. So we're going to have to wait till November. And then we're going to have to wait until wherever Planet 9 is in sort of the field of view for Virubin. So stay tuned. I would say within a year, we should either find it or rule it out. Let me highball through some questions now. There's a lot of questions. Wilksy1, with Atlas Comet currently near Mars, is there anything it suddenly did that would make you view it as an alien? Sure, lots of things. If it suddenly changed its speed, if it gave a chemical signature of something that is just utterly unlike a ball of ice, gas, and rock, then yeah, you would view it as alien. But right now, it's just a comet. It's doing very comet-like things. And so anybody who's saying that it is an alien spacecraft or believes they have evidence that it is an alien spacecraft is seeing more into this than they should. And it's going to pass by through the solar system and head off perfectly along a normal trajectory and be forgotten until the next asteroid or comet shows up and people say it's aliens. And it will also not be aliens. Billions and billions of stars. Will we be able to spot 3I Atlas through a small telescope before or after it reaches perihelion? Yeah, I'm not sure sort of what its maximum magnitude is going to be, but people are seeing it. I think it's like in the 18s right now. Let me find out. What's its current 3I Atlas magnitude? So it's currently 13.7. So it should get to magnitude 12 in October and November. And magnitude 12 is visible in a small telescope. No problem. Like, let's see, binoculars even? Mm, 12. So if you have a pair of binoculars and you know where to look, you might be able to see 3I Atlas. Paul Wilson, what happens to water particles released from a comet? Do they just hang around in a long tail forever, or do they clump together? Would they damage a fast spacecraft flying through the trail? So the water particles are being driven away by the radiation pressure of the sun and the solar wind, and they are just flying out into the universe, carried along by the solar wind. Would they damage a spacecraft if it flew through them? No. I mean, maybe if a big chunk hit a spacecraft, but we actually have had a mission called Stardust that flew through the tail of a comet to collect particles and then brought those particles back to Earth that scientists were able to study them. Owen Brown, I have a question, and all my questions are excellent. With all the resources in the solar system, how many O'Neill cylinders could be built, and how big? I don't know. Take the mass of the solar system and divide it by the mass of an O'Neill cylinder, and that will tell you how many. What's the mass of an O'Neill cylinder? Let me find out. I'll get you started. They would be 6.4 kilometers long, 6.3 kilometers in diameter, and 32 kilometers long. So billions of tons. We can still build a lot. There's a lot of stuff in the universe, in the solar system. Lorcana Dude, what are the chances that we missed a lot more interstellar items before the launch of the latest telescope? I mean, really good. It's estimated that there are thousands, if not tens of thousands, of interstellar objects passing through the solar system right now. So that we missed tons of them. And it's only in the last couple of years our all-sky survey telescopes have gotten really good. Atlas is from an all-sky survey telescope. And Vera Rubin is going to find probably 6 to 12 of them a year. So as we get better and better at watching the entire sky for anything that's moving, we're going to turn up all kinds of interesting things. Ramshambo, how long will the dead Akatsuki spacecraft stay in the orbit of Venus? I don't know what its altitude is. So maybe this is a question that I will do some research afterwards. Jay Lambert, given that the moon has much lower gravity and 2 landers have already toppled over, what is SpaceX's current design for its lander? And does it take into account how tippy things are in lower gravity? Their plan is to not fall over. Their plan is to be very careful. Their plan is to engineer their lander so that it doesn't have a problem. That it's a very tall, very top-heavy who knows how top heavy it's going to be. Maybe all the fuel's going to be down at the bottom and it'll be, more bottom heavy. But it's going to have little legs that are going to pop out the bottom of the rocket. And hopefully, unless there's it should land very carefully on the flattest place that it can find. They'll research the landing site carefully, and then hopefully it will land. But yeah, it seems like it would be, seeing how various landers have already fallen over, they better be very, very careful. Hair of the Dog. In space simulators, you usually have to do 2 separate burns to get to orbit. A launch with a gravity turn, cut engines, and then a circularization burn. How is that in IRL? Only needs a single burn. I'm not sure you're seeing only a single burn in real life. So this idea of circularization. So the gist is that if you launch with your rocket, then you're going to go into a ballistic trajectory. Now, that ballistic trajectory could be very fast and take you very high up or take you very far around the Earth, but it's going to eventually bring you back to the Earth because one node on the orbit that you're carving out goes through planet Earth. And so the way that you have to fix that is that once you've reached your apoapsis, you've reached the high point of your orbit, then you fire your rocket again, and then you circularize the orbit. I'm making the shape of what happens when you play Kerbal Space Program. And so you have to do two maneuvers. You launch off the Earth, or you launch off Kerbin Prime or whatever, and then you get up into orbit. And then once you've reached, you coast up to your apoapsis, and when you've reached your apoapsis, then you fire your thrusters again and you circularize your orbit, and now you're in orbit. It takes two maneuvers. And that's why Superman can't kick you into orbit, right? Superman could kick you and you would be on a trajectory that would still bring you back to the Earth. It's only if you had a rocket engine and he kicks you into space and then you fire your rocket engine, can you actually circularize your orbit. Now, it could just be that it's a very smooth process, that they are, they're taking off and they're firing the rocket and they're just constantly changing their trajectory until it becomes a circular orbit. And it looks like it's just one burn, but it's continuous across the entire process. But there are lots of times where people have to do, where missions have to do, like they'll go into, they'll do that circularization burn, or they'll stay in orbit around the Earth for a couple of orbits, and then they'll do a burn to go to the moon or Mars or whatever. We saw that in the Apollo missions. Casey Ream, is the giant centrifuge still part of astronaut training? How much time is dedicated to that? I would assume so. I'm not sure how many new astronauts. They did a lot of the research on, when they had those giant centrifuges, that was for them to try and figure out what were the effects on the human body, because they just didn't know what the forces were going to do to the human body. And so now they do know. And a lot of the astronauts are test pilots that they have trained to handle high G forces, and there's certain suits that you can wear. There's certain exercises that you can do, weightlifting and so on, to keep yourself in good shape to be able to handle the forces of the high G. So I don't know if they must still put them in the centrifuges for them to feel what the forces are going to feel like when they're going to go to space. But I don't actually know. Goat Lord, would you be able to see Saturn from the surface of Titan, or is the atmosphere too thick? I don't know. That's a great question. I have no idea. Kojam, what is your favorite question that you've ever been asked during a live stream? That one. That question I just got asked. Could you see Saturn from the surface of Titan? Mikhail B, what would happen if a rocky planet reaches its top limit in size? Would it ignite like a star? Assuming like a rocky planet was made with 10 times the mass of the sun, it would collapse into a black hole. Kevin Zelaya, what are some upcoming lunar missions that are not Artemis? The Chinese are continuing on their Chang'e missions, and they're going to get to the human landing in the moon on 2030. And then you've got a bunch more of these commercial missions to the moon that NASA has been funding. So, there was Blue Ghost, there was the Odysseus, the Intelligent Machines? Yeah, the Intelligent Machines missions. And so there's a bunch more of these that are planned over the next couple of years. There should be a lot. And in fact, we just learned that the Viper mission has been picked up again and is going to be going to the moon on a Blue Origin launch, which is apparently a rocket. That's a company. Mr. Transposen, not a silly question, but what is space? Would confine be the opposite? Space is it's like you can decide what space is. There's like all the universe, and because there's not a high density of stuff in the universe, then people use the term space. There's a lot of space out there, and there is. So, where does it begin? Where does it end? When is it space and when is it a planet? These are all just sort of purely subjective decisions that people have to make. Max Brooks, what does the data that space telescopes look like when it's scanning an area of space? How does it determine which infrared light is coming from each forward-looking point? So, I mean, for a regular telescope, like with visible light, telescopes use something that's very similar to what you have in your phone camera, right? You have a 30 megapixel camera, and the megapixel comes from the number of pixels that are this sort of grid that the camera is sort of putting the image onto. And so photons are coming through the lens of the camera. They are hitting these pixels in the CCD in your phone, and they are filling up, and then the phone is determining what the picture is. It's a very rough description of how this works. And telescopes do the same thing, which is that they have, in many cases, the exact same kind of technology. The same sort of CCD that is used in your phone is used in telescopes. They're just much, much bigger, right? Like the camera in the Vera Rubin is 4 gigapixels. Like, it's ludicrously large. It's just, lots of pixels times lots of pixels, very big area where it's being able to receive them. Now, the sort of the wavelengths of light that the telescope is sensitive to depends on the filters, on how you block light from getting into the telescope, or which kinds of light you're attempting to reflect, or which kinds of light your CCD is sensitive to. And so you can put a filter in front of a telescope, like literally a thing that goes in front of the telescope that blocks all the light except for photons of a very specific wavelength. Like, you only want to let the blue photons in, or you don't want to let the green photons in, or you want to let the photons from the hydrogen radiation, or you only want to let in certain wavelengths of infrared light. You can control what kind of light comes into the telescope. They hit the CCD, and they're able to produce an image based on that. Gort from Mort, what experiments have been done to test panspermia theories? Lots of experiments have been done to test panspermia, in that, we know that microbes are hardy. They're able to handle various parts of the journey from world to world. They're able to handle you're not actually going to crash an asteroid into Mars to find out if microbes can handle it, but the kinds of heat involved, the kinds of forces involved, and the amounts of time that are involved that a microbe, the amount of radiation that a microbe is going to experience when it's traveling through interplanetary space, the kind of heat that it's going to experience as it's entering the atmosphere of the Earth, and when it hits the ground. So, you can't perfectly perform the experiment, but every part of the journey seems to be within the tolerance of bacteria to be able to go from world to world within the solar system. Aaron Calhoun, could a comet come from a star from a different galaxy? Yeah, theoretically, sure. There are almost certainly comets here in the Milky Way that came from another galaxy, not just another star system, but an entirely different galaxy. We know that there are stars that are being ejected out of the Milky Way they're heading on escape trajectories out of the Milky Way. And so they're probably the same thing in Andromeda. There are stars that are being ejected out of Andromeda, and some of them are in the Milky Way and have already made the journey from Andromeda to the Milky Way. And they might have brought comets with them. So there are going to be intergalactic comets here inside the Milky Way. They would be really hard to know the difference between an intergalactic and an interstellar comet, but they're out there. And so if you run the numbers, an intergalactic comet has probably passed through the solar system at some point in the past. Poe 9320. What do you think the Titan dragonfly will find around oceans of liquid methane? they're not going to the oceans of liquid methane. So Titan Dragonfly is going to be sticking around the equator and not going to the seas, which I know sounds crazy, but that's just the plan. Sean Mann, going to toilet in space. How does that work? Is it a more strenuous task? So the problem is that you're not sort of, gravity isn't pulling you down to your toilet, that gravity isn't pulling the things that you are pushing out of your body down. And so everything wants to float. You want to float. Your toilet wants to float. Your pee and poop want to float. And so the whole job of making toilets work in space is all about controlling all of that stuff. The vacuums are involved. It is a very complicated operation to make a toilet work in space. And imagine when they break and they spill. Cliff Holzer, if we were surrounded by civilizations at the tech level of Mars, how would we recognize that the civilization to be found? I'm not sure what that, what the tech level of Mars is. Tech level of Earth. Okay, so if we were surrounded by civilizations with the tech level of Earth, how could we recognize these civilizations? I mean, it would be really hard for us to be able to recognize another civilization at the technology level of Earth. There is very little that humanity does to send a signal out into space that we could detect. There's a couple of things. We're about to have telescopes, radio telescopes, powerful enough to be able to detect the air traffic control systems of Earth. So that's a thing. We could point, say, the square kilometer array at a nearby star system and detect the air traffic control system there. That would tell us that there's an intelligent civilization there. The strongest signal that we've ever sent out into space was the planetary radar system on the Arecibo Observatory. So back when it was scanning asteroids, it's this huge dish and it was firing this big beam of radio waves out into space that would then bounce off of an asteroid, and then they could use that to map the shape of the asteroid. Very concentrated. And so it's estimated that we could detect the beam from that planetary radar out to tens of thousands of light years away. So theoretically, if there's some civilization and they are mapping asteroids in their solar system and we happen to be on the other side of that beam, we could detect their presence. But apart from that, there's, it's thought that maybe we could detect the presence of chlorofluorocarbons, like greenhouse gases, in the atmosphere of a planet like Earth if it's really close to us. But apart from that, we just don't have the technology right now to detect the presence of even ourselves. So we have to come up with better telescopes. Silas Miller, Fraser, what sci-fi book best describes our world in a few hundred years? The Bobiverse book 1. Now, I wish the Bobiverse, well, there's parts that are pretty horrible about the Bobiverse book, but the Bobiverse book is fantastic. It's funny. I recommended that my son read the first book, We Are Legion, We Are Bob. And he's like, yep, this is my kind of book. I love this book so much. They're such great books. So if you haven't read them, the Bobiverse books, read them. They're so good. What sci-fi book best describes our world in a few hundred years? So it's really tricky. Like, if you want a realistic answer for what the future holds for humanity, we're at a turning point in the history of our species. And it is almost impossible to make any realistic predictions about what the future holds for our species or for our planet, because we're in the process of creating a life form, a new mind, a new species that has the theoretical potential of being smarter than us, which is artificial intelligence. And so, whenever a smarter species runs across a dumber species, it doesn't work out very well for the dumber species. And so if we actually create a smarter species than ourselves, there's a significant chance that we will not survive the encounter. So I would wait, a few decades. If we get to a place where it turns out building superintelligence is impossible, or we've solved the problems of alignment of artificial intelligence, where we're like, okay, here's how we cage God, right, to do what we want. Until we've solved those, either solved that problem or demonstrated that it's impossible, that the human mind is the smartest possible mind, then the future is unknowable. And so there is no science fiction story that gets us past the singularity that feels, to me, realistic. There's lots of stuff that I really love their futures. And it's like, if we never develop artificial intelligence, then the expanse feels very realistic. If we never develop artificial intelligence, then the Matrix feels very realistic. Although there's a lot of artificial intelligence in the Matrix. So we just don't know. We just don't know. Yeah, it's tough. James Leatherwood, I disagree with your AI sentiment, but that's okay. It's fine. It's fine. I mean, I think there are, the people who know the most about AI are concerned about it, right? The godfather of AI, Jeffrey Hinton, Yoshua Bengio, the most cited computer scientist in history. There's a lot of people who think, and the argument is very simple, right? Which is that we don't know how AIs work. We don't build them, we grow them. And that when you make something that is more intelligent, there's no guarantee that it cares about you anymore. That's it. If you don't know how, if you can't guarantee how it's going to work, then we don't know what it's going to think about us. So it's I think for most people, that's enough. Like, that's enough of an argument to go, yeah, we should probably be careful. We should maybe set some rules so that people don't just run headlong into building something that is smarter than us, that there are risks and we need to be cognizant of those risks. Melinda Green, I'm not worried about superintelligence in itself. I'm worried about what its makers and its operators use it for. Yeah, like, at the very least, like, if you interact with AI right now today, you are starting to have a genie in your computer where you're like, design my meal plan, program this code for me. And then eventually it'll be, build me something out of 3 dimensions, build me a new computer, build me a new thing, humiliate my enemies, right? Like, what happens when everybody on Earth has access to a genie, a magical genie that can fulfill their wishes? Will our wishes clash? Will somebody out there, like right now, when somebody has, thinks that I should die, they will email me death threats. But could there be some future where they can make those plans become real? Just they say to their genie what they want done, and they will take effect in the world. So at the best possible version of this is that we have a world of billions of people who have competing genies to fulfill their wishes, and their needs are going to be in conflict with each other. And then the worst possible world of that is that the genie has desires of its own, and they don't include us. Jamie Doe. I've been thinking about the Fermi paradox lately. If I were an alien, I wouldn't want humans to know about me given our record. Could you give me a reason why they would want us to know they exist? I mean, we can't possibly imagine the psychology of different aliens. So, um, think about there's the people on this, is it the Sentinel Islands in the Indian Ocean who live on this island, and they've made it abundantly clear that they don't want any interaction whatsoever with modern society. Like, obviously they see our airplanes fly overhead, they watch our ships go by, but they throw spears and kill anybody who tries to land on the island and interact with them. And so we respect that and we let them go about their lives. But every couple of years, some idiot kayaks onto their island and gets killed because they just can't help themselves. But I can fix them. I can bring them forward into modern society. I can convert them to my religion, whatever. And so I think we have to assume that the aliens are going to be the same thing. Some of them who they admire us from afar, but they're just too nervous to reach out and say hi. Others just absolutely don't care anything about us. They just want us to. They want to proselytize their space religion and bring us into the fold. And who cares how, they know that their military can totally handle anything that we can do. And any infinite number of different psychologies that will be happening from an alien civilization. They are alien. And so we can only predict large scale possibilities of how they want to behave. And they probably won't behave the same because they will be alien to each other. And so I don't think we can ever say, it's like a trap to always say, I don't think the aliens are going to do X because aliens don't want to X. We don't know what they're going to be like. Some will be like that. Some won't be like that. There could be millions of them out there, and each one can have its own special, complicated, inscrutable interests, which will either are compatible or incompatible, incomprehensible to our vision of the universe. So yeah, even we could be super sweet to them and they would never want to have anything to do with us. Others, we could be super mean to them and they would still want to hang out with us in a codependent relationship. Paige Potter, what is a question that you are rarely or never asked but wish you were asked? I have been asked every single question. So there is never I can't imagine a question that I haven't been asked. I don't have space in my brain to go, come on, ask me the question. Somebody, please. Like, we are so far beyond that. What are we at? I answer 100 questions a week for 45 weeks. what was that? 4,500 questions a year. And I do that for years. So I've answered, 20,000 questions. So I have no idea. Church discography. How long until we can get robot dogs that are indiscernible from the real ones? I mean, partly it's going to be a while, but there was a video that I saw of some Chinese engineers that had a human face that was making expressions, and it was so real. Like, it looked real. And it's kind of like, it's really just how good the servos are going to be, and then the behavior of the servos to mimic the movements of muscles. So, yeah, we may very well get to a place. I mean, the robots are becoming a lot more dexterous at this point. I don't know if you've seen robots that are, you can kick them and they don't fall over, or they fall over and then they do some kind of kung fu kip up and get themselves back up onto their feet, or they're running and they're jumping. And I bet you we're going to be watching soccer games with robots in the future. We are accustomed to robots being, brr, crump, do the robot, but they could very well be incredibly dexterous and graceful, right? We don't know what the limits of the machine are. All right. I think I'm going to wrap it up here. Thank you, everybody, for hanging out. This was awesome. What a crowd. What is happening? Right. So a huge thank you to the moderators. Special thanks to Zapfan for hanging out, even though it's early in the morning for you. Thanks for posting the questions. Thanks in advance to Chad and Anton, who are going to have to watch this nonsense and sort it into useful videos that I can then review later on. And we'll see all of you next week. Thanks, everybody. Man, I got lots of energy. I could have gone for another hour, though. But I've got to go.